This reaction looks at spontaneous reactions and Gibbs energy. A spontaneous reaction is that one, once started, goes to completion. For instance, the burning of a match. What factors drive this reaction? First of all, one thing spontaneous reactions tend to have in common is that many of them tend to be losing energy. They're exothermic or negative delta H. They also tend to gain entropy, positive delta S, or increased dispersion of matter and energy. I want to look at various combinations of these factors and make some comments about their spontaneity. So as we have, in the first case, losing energy and gaining entropy, both of those factors coincide with the factors that drive a reaction. Reactions that have both things in their favor will always be spontaneous. Conversely, if it has both things against the driving forces, they're endothermic or negative delta S, they'll never be spontaneous, no matter what temperature I run the reaction at. What if we have a reaction which has a negative delta H and a negative delta S? In that situation, we have one factor, the enthalpy factor, in its favor, and the entropy not. These reactions will be spontaneous at low temperatures. In my last situation, where both values are positive, these will be spontaneous at high temperatures. One way to remember the last two scenarios is to look at the sign for a moment. Negative and negative makes me think of something low, and positive, positive makes me think of something high, hence the low temperatures and high temperatures. In those last two cases where we have a reaction that could be spontaneous depending on temperature, a useful tool to resolve this dilemma, whether a reaction is spontaneous or not, is Gibbs energy. And we can calculate that two ways. First of all, products minus reactants, and again, consulting the table in our IB data booklet, which actually gives us the Gibbs energy of many substances. A second technique is to calculate Gibbs energies to take a look at the enthalpy change minus the temperature in Kelvin times the entropy change. So it would use these two values that are in the table. A negative value for the Gibbs energy indicates a spontaneous reaction. We can see here why temperature now has an effect on spontaneity. If we have a reaction that has a favorable delta S, we can increase the temperature to increase the entropy factor. Similarly, if the entropy is not in our favor, we can decrease its effect by lowering the temperature. I'd like to look at an example that uses these equations. Consider the evaporation of ethanol at room temperature. Both factors are positive. So, in this situation, the enthalpy change is not in favor, but the entropy change is. So this would be spontaneous at high temperatures. Is 25 degrees Celsius high enough? Well, let's turn to this equation to solve that. I'm going to firstly substitute in the values. You'll notice that I've changed the kilojoules into joules to get consistent units between my enthalpy and my entropy. The second item I've changed is the temperature was in Celsius. I converted it to Kelvin. Solving now for delta G, or the change in Gibbs energy, I get positive 5900. So this reaction would not be spontaneous as it's greater than zero. What temperature range does this reaction become spontaneous? So again, I'll start with that equation. And make note that the transition between being spontaneous and not spontaneous is going to occur at zero. So I'm going to let delta G equal 0 and substitute in my values. So the only unknown now becomes my temperature. I rearrange it now and get the temperature by itself. So I finish with 352 Kelvin or 79 degrees Celsius. And I was also asked to give a range. Recall that earlier we identified with both signs being positive, spontaneous at higher temperatures. So it would be 79 degrees C or higher, which by the way is the boiling point of ethanol.